All right. So, hey guys. So I've got a cool guest today, Pranav Gokhale, CTO, Infleqtion. Thanks for taking the time to talk to us. All right. So first question: as an undergrad, you wrote a paper on the quantum square root implementation. And what I found kind of crazy about it is that instead of doing like directly the square root, you did 1 over the x, and then you did 1 over the square root, and then like combine this together. I was wondering if you could give us some idea of why it works better that way.
Yeah, sure. Thanks for reminding me on this trip down memory lane of this project from a while ago. That was one of my first really diving deep into quantum computing and quantum circuits and resource estimation. So the short answer, and I'll just unpack it a bit more, is to get root x. One way is to, exactly as you said, get 1 over x and then 1 over root of that quantity, which if you apply it together and compose, you get back to root x. So first off, why is that quantity valuable? It's because a lot of applications that we care about, whether in numerical analysis or differential equations, et cetera, rely on computational square roots. And one of the caveats in quantum computing, as many of these audience of your show may know, is that the math for quantum circuits has to be reversible. And so that makes a lot of unusual surprises in quantum computing. So for instance, you can't do something like an AND gate. The Boolean AND operation is a lossy process. You have 2 inputs and 1 output, so that's just fundamentally lossy and irreversible. So on the other hand, there's ways to patch up existing non-reversible logic gates and make them reversible. For the AND gate, one way is to flow through one of your original inputs along with the output of the AND, and then that way you can have reversibility. So what does that have to do with the...
Like, sorry, Jake, you know which one disappeared by looking at like the extra one?
Exactly,
Okay.
yeah.
Sorry.
No, it's a good question. Another good example of this is the controlled NOT gate. The C NOT gate is an exemplar of this because on one of the output wires, it's computing I guess an XOR gate, and then the other is computing the original copy of the first input. And so that's an example of taking the XOR gate and making it reversible. So back to square root of x, it turns out that if you try to go directly from x to root x, you end up, at least with the algorithms that were known at the time, which I'm sure have advanced dramatically since circa 2013, there weren't great single hop reversible ways to get to root x. I mean, in principle, it's reversible because you can just square the number modulo whether it's the positive or negative. But it was expensive to get to root x, whereas there was a known way to get 1 over x and a known way to get 1 over root x that were relatively cheap. They used certain reversible circuitry hacks. One of them, I believe, was basically Taylor expansion of a ratio. And so that mathematical hack, coupled with itself twice, let us get what we found was a cheaper way to root x than trying to do it directly. I will also confess that I suspect that the math, again, the algorithms have evolved dramatically since 2013. So if we were to do it again today, I'm guessing there will be better ways to get to root x, but that was the project that got a lot of my real research level excitement in quantum computing started.
Nice. That's really interesting. Thank you for the extra details of the mathematics. Okay, so let's skip forward to, you did a postdoc at Argonne, that's correct. Can you tell me your thought process and like adventure between like finishing your postdoc and then like ending up at Infleqtion? Like at what point did you decide you want to be your own boss?
So I caught the startup bug in, I'd say, 2014 in college, and it was maybe a year after that square root paper. I had the opportunity to visit Silicon Valley to meet with a lot of the most exciting entrepreneurs of our time. I think Jack Dorsey was one of them, of Square and Twitter fame, Peter Thiel, a renowned venture capitalist, et cetera. And I think that trip, which was organized through my university, planted those seeds of doing a startup is one of the most effective ways to bring technological revolution out to the markets much faster than it otherwise can happen at very large companies or in university exclusive environments. So it wasn't necessarily about being my own boss. And in fact, I now have an absolutely wonderful boss, Matt, who I like to work with, so much as wanting to be in a position where I could help technology evolve and get out to a lot of hands much faster, especially in good ways and positive ways. And so when I came to grad school, I already was coming in with a little bit of this mentality of how can I commercialize research and take it out of the realm of just university lab environments to something that eventually reaches products. And even to Argonne, my postdoctoral fellowship was very interesting. It was a Oak Ridge-based ORISE fellowship is a technical term, but it was structured so that I could be working on a cooperative research and development agreement with Argonne National Lab to then commercialize my research into a company, Supertech. And then finally, the conclusion of that entrepreneurial journey, or rather the start of that entrepreneurial journey in many ways, was realizing that our technology on the software side was very compatible and able to work back and forth with the hardware technology that Colt Quanta was building, which was the hardware name predecessor to Infleqtion. And so we joined forces in May of 2022 and have been working together closely ever since. In 2022, we changed our name to Infleqtion. And then just 2 weeks ago, as you know, we went public, which was quite exciting. And now we're ready to continue to deploy our products to market and have a lot more money to do it with, which is exciting.
How do you think things are going to change, or if anything's going to change now that you're public?
One of the main things that happened that was exciting in the plan, the pathway of going public, was we raised $550 million, which is quite a lot of money. And we've...
Sorry, can I ask how many employees in the company about?
I want to say roughly 200 something,
Okay, yeah.
but plus or minus 50, I forget the exact number. But I'm sure it's findable in some documents around 200 or so.
So 550 million for
Yeah.
200.
And we'll be growing, but I guess the context is our last round of funding, our Series C, was $100 million, which is still a lot of money. Our previous round was also about $100 million. But this is a new order of magnitude of funding, and what it means, to quote Matt, our CEO, is that one of the important legs of our stool as a company is the capital markets. Do we have the financing solved to really invest deeply in our technology and our commercialization? And I think we have done a phenomenal job through this going public process to de-risk that leg of that stool. And now we can really turn our attention towards the technological innovation side and then the execution side, both of which are important. So back to your question, I would say what this going public process has done in my eyes is enabled us to fulfill our mission and our destiny in ways that previously we would have needed to potentially raise more money.
Nice. So I guess, would it be fair to say that you can not maybe take bigger risks because you know what you're doing, but like take on bigger challenges?
I think that's a fair characterization. And so, for instance, we announced just a few weeks back that we're sending quantum to space. And that's incredibly exciting and in ways that honestly I didn't appreciate until joining the Colt Quanta merger with my startup Supertech. But space is not cheap. It's expensive to build the engineering mindset as well as the level of scale to think about doing exciting things in space. And so those kinds of big picture bets, I think we were perhaps a bit shy to take before we had this level of funding come in, and now we can really think about quantum at the next frontiers of space, of AI, et cetera. So yeah. This is a new type of glass cell that we've been developing in conjunction with this NASA program to put quantum in space. It is titanium welded to glass, which is an extraordinary engineering feat, and it's done using a very large ultra-fast laser system. And the reason this is exciting is that this is going to enable these quantum sensors to go into space and withstand the launch pressure of a rocket going up, and also maintain an extraordinary vacuum once in space.
So this is the gas that the Rydberg atoms live in, I guess?
Bingo. So you'll imagine there's other stuff around this too. This will eventually be a closed environment, but yeah, this is where we put our either not just the warm vapor of atoms for quantum RF and Rydberg, but also ultra cold matter, even as cold as Bose-Einstein condensate, et cetera.
Nice. So let's talk about some of your technologies. The first one is, I don't know if it has a name, but it's the like your quantum inertial sensors. I was wondering if you could talk to us a bit about how so as I understand it, the inertial sensor knows its acceleration, and then you can integrate over that to get velocity, and then integrate over that to get position, and now like you know where you are. But each one of those integration steps, like you get a bit of drift, and like especially the longer you do this for. I was wondering how you guys plan on mitigating that.
Sure. Well, the first answer is basically exactly what you said, which is that position is the second integral of acceleration. And so what that means is just tiny improvements to your measurements of acceleration have a massive downstream impact on the integrated errors or lack thereof for position. So going back to why do we think that quantum is a good technology for inertial sensing, it's that when you only rely on classical inertial sensors, there are some very fundamental expectations of how much precision and accuracy they can give. There's terms like strategic grade inertial sensors, et cetera, where we think there's a path to getting quantum accelerometers, quantum rotation sensors that do far better than what strategic grade navigation systems can do today. Now, to your point, even that is not good enough forever because any finite amount of error is eventually going to accumulate, and in fact accumulate at a second integral level. So our view is that much like quantum computing, we think about hybrid systems where you have your QPU co-processing with GPU and CPU, et cetera. We do think that there's going to be important integrations of internal references like a quantum inertial sensor with external references, including classical references, including GPS systems and GNSS systems. So for instance, if you can go for 6 hours before your error becomes too large and then have an expectation that 6 hours later you have some signal either from a standard conventional system like GPS or something like a signal of opportunity, something that wasn't designed to be a navigation system but can be, or even star pointing. For instance, a lot of aircraft today are able to use computer vision algorithms, et cetera, looking at the celestial sphere and use that as their way to give that absolute refix their position. That's where we see a lot of this technology evolving, which is combine really good what's called dead reckoning of minimizing to the extent humanly possible, quantumly possible for the accumulation of drift, and then eventually patching up with some absolute references. And then maybe just to dwell on that piece, I mentioned that those can be classical references, but in fact, quantum can be a part of that too. So for instance, we make atomic clocks, which you might get to as well. And those atomic clocks are a really important part of how a new terrestrial-based network, for instance, of positioning systems that are resilient to attacks on weak satellite signals, that would be underpinning a quantum network, or rather a classical network of quantum timing devices. So even those classical references, I think there is a role for quantum sensing or quantum computing to play.
Nice. Another cool technology that you guys have is I think it's called SqyWire. It's hard to, there are all these Q's in there. So, and I think you've described it before as a sugar cube sized quantum RF broadband receiver. I was wondering if you could tell us like the physics behind it as if we were like fifth grader to like high school.
Sure. So let me start with classical RF receivers and then explain what's different about the Rydberg SqyWire quantum RF receiver. So first, for classical radio frequency receivers, if you want to listen to a frequency, a wavelength of length lambda, meaning the wavelength is lambda equals 100 meters or something, in general, the optimal, so to speak, way to listen to that wavelength is to have an antenna that is lambda over 2, so in this case 50 meters long. And that's basically long enough that the EM radiation can, I'm going to be imprecise here, but you said fifth grader, slosh around the antenna effectively and effectively be absorbed. If it's too short, it can't effectively be absorbed. And in fact, for the high school end of that spectrum, there's a really interesting theorem and limit called the Chu limit from the Nobel Prize-winning physicist, I think Stephen Chu. And it basically shows the math of how if you go too small beyond lambda over 2, you start to have issues with your Q factor of your antenna. So that's kind of been the axiom, the fundamental axiom of RF receiving, RF sensing for ages. What quantum RF does is we use Rydberg atoms. These are atoms where the electron is extremely excited, almost to the point of ionizing off, falling off the atom, but not quite. And in that Rydberg state, thanks to a deeply quantum mechanical phenomenon called EIT, electromagnetically induced transparency, there's this superposition phenomenon that takes place. And forgive the fifth grader who probably doesn't know, but maybe the high schoolers now know a little bit about qubits being 0 and 1. There's a superposition phenomenon that allows us to tune this RF sensor to be extraordinarily sensitive, transparent, in the right frequencies to whatever wavelength we want, from about kilohertz to about terahertz frequencies and the implied wavelengths of that. And what's exciting about that is, for instance, if I'm talking about the lower frequency end of that spectrum, let's say about 3 megahertz, 30 megahertz, HF signals, et cetera, those have wavelengths that are many, many meters long. That's why I picked 100 meters. And traditionally, I would have needed a 50-meter antenna for that 100-meter wavelength to actually optimally listen in at that transmission frequency. But with this quantum RF receiver, all of those wavelengths are enormous compared to the atom, even the Rydberg atom. And so what we're really doing is kind of decoupling the scaling laws of lambda versus lambda over 2 to what the atoms are doing. The atoms are tiny, and so they're just not trying to absorb the radiation per se, the way that a traditional antenna absorbs radiation.
No sloshing.
No sloshing. They're just sensing the actual electromagnetic field in place, the electric field in place. And so that's a very different paradigm. It doesn't actually quite, it's subtle. It doesn't violate this Chu limit from many decades now. It just is a different paradigm of how we listen to RF transmissions. It's not absorbing, but it's rather sensing. And so that has opened this world of possibility where traditionally we would have thought that we need lambda over 2 receivers lengths. Now that can be shrunk to a device that just has a vapor of atoms inside. And that device can be quite small. It can be the size of a sugar cube. It is connected to a rack of electronics, which is about the size of a mini fridge. But again, that's tiny compared to a very long antenna.
That's cool. Yeah, I think I read somewhere that like the further out the electron is, the more susceptible it is to polarization. To like if n is the how far it is, it's like to the power of 7 or something crazy like that.
Exactly.
So it's like it's super sensitive, like when you're basically about to fall off the
And
atom.
maybe just to pass on that, that's also true for our quantum computer. The way that we do gates between neutral atom qubits is with the same Rydberg physics principle. And it's, I think, a n raised to 6 scaling, which is a massive, massive polynomial, but it's, well, technically it's 1 over n raised to 6, but it's really cool how there's these new scaling laws that have emerged thanks to the physics of Rydberg atoms, these highly, highly excited electrons.
So let's talk about your the quantum computers you guys have. I think you call it Sqale. You previously talked about how AI and machine learning are a possibility for future quantum computers. I was wondering if you could expand on that. You previously said how it's really going to work out if you mix it with classical, advanced computing, high performance computing. But I was wondering if you could elaborate on that.
Yeah, sure. Let me give you 2 examples, maybe 2.5 examples, actually. So I'll start with the half example, which is how classical HPC and AI compute fabric, like GPUs, play a part of every quantum algorithm, whether that quantum algorithm is applied to cryptanalysis or to material science, et cetera. And that's because for a quantum computer to operate, it needs to have right next to it a stack of classical electronics, classical compute, that measures what are called syndromes, the issues of errors that have emerged on the quantum computer, and then solves this inversion problem of going from the errors or the syndromes to the actual errors and correcting them.
Is that quantum tomography or?
It is related to quantum tomography. I would think of quantum tomography more as like, once I end the computation, where did my qubits end up?
Okay.
But this is more at the level of the program itself. What is the tomography, if you will, of where were there issues in the program? Where was there a bit flip error, a phase flip error, et cetera?
Oh, okay.
And that's called decoding. It turns out that the GPU stack is extraordinarily good, and in fact, neural network decoders using AI are the leading ways to most efficiently, or rather most accurately, decode error. So one answer, the half answer that I'll give you is, regardless of the type of end workload, there's going to be tremendous amounts of AI and classical HPC sitting right next to the quantum computer. Now let me go to where the quantum computer itself can be useful for AI. The first example I'd be particularly passionate about is something called contextual machine learning, or CML. This is a technology that we debuted at the GTC conference from NVIDIA last year, just about 11 months ago. And it stems from this observation that there are certain data sets, you can literally think of them as, for the person who's done some AI programming, as a PyTorch data set, a tensor data set. And these data sets, it turns out, can be exponentially harder for a classical computer to do inference on than a quantum computer. And what makes these data sets important is that they leverage a principle called contextuality of quantum mechanics. Now, this is a very, very deep principle within quantum mechanics. It's in many ways what explains why quantum computers can get sped up. But at the gist of it, contextuality is really a statement about how qubits have memory of previous measurement outcomes. And if you apply a sequence of measurements, then that has certain statistical properties that become available downstream, if and only if you have a quantum computer, at least efficiently. And so let me be a little bit more concrete with you. What we showed is that if I give you a data set of contextual measurements, and it doesn't even matter what that is, it's just, at the end of the day, it's a PyTorch data set. If you try to learn on that data set with a classical GPU model that has a linear amount of memory, it is bound to fail and fail catastrophically. On the other hand, if I use a quantum computer that also has a linear amount of memory, we can prove that the quantum computer can learn that distribution exquisitely. And this is a very technical term that I'm using, so I just summarize it as there's certain learning tasks where a quantum computer is known to outperform any possible classical model on an equal memory basis. And in fact, memory is the bottleneck for a lot of modern day machine learning algorithms. If we look at GPT-4, GPT-5, et cetera, the amount of memory that they have is only a few kilobytes in terms of the sizes of their hidden states. Each hidden state is applied what's called autoregressively, which means it's applied many, many times. So in aggregate, that spans gigabytes, terabytes, et cetera. But per unit of time, you've got a hidden state size of about a few kilobytes. And so going back to quantum computers, I think quantum computers give us this way to take existing models that have been memory bound, where we can't go much bigger in memory because that has some really bad implications in terms of the runtime of that model, and have this kind of backup friend of a quantum computer next door that helps to address certain high memory tasks. That doesn't mean that if this is a cure-all for AI. A lot of tasks don't require that much memory, but a lot of the frontier of AI does require a lot of memory. So that's the main one that I'd give, and maybe the quick side other one I'd give is a lot of the frontier of material science also boils down to, can we have certain computations, some world models of the underlying physics of materials? World models have entered the AI discourse quite dramatically in the last 6 months or so, and we think that quantum computers give you a nice way to build a better world model for the dynamics that govern modern day AIs, or rather, the real world, which is trying to be captured by AI. And so that's another direction where I see QPUs playing a role.
I read that, or his name is escaping me now. Richard Feynman. He always talked about how if we want to model the quantum world, we need a quantum computer. And it sounds like if you want to do AI on quantum systems, you need a quantum computer for that.
Bingo. And it's been surprising in some ways how far certain models have gotten without a quantum computer, but they have started to reach a lot of their saturation of limits. And a lot of the frontiers of where, for instance, material science, chemistry, drug discovery problems have stopped making progress is when they run into fundamentally quantum mechanical phenomenon like electron-electron interactions, et cetera.
Yeah. As viewers of this channel can tell, we are big fans of science outreach. I know that Infleqtion does a program called Teach Quantum, and then something called Albert, which is related to cloud quantum computing. I was wondering if you could tell me about those two projects and any other outreach type programs you guys have.
Sure. So I'll have to confess, I know we have done a lot of things with Teach Quantum. What I can perhaps personally say is that in this office in Chicago, which is where I'm based, we've been very active in terms of outreach to local schools, high schools, but also elementary schools. I'm a volunteer for Hour of Code in the years that's happened, which is where we've gone and taken other employees to local elementary schools, because it's never too early, we think, to start learning software engineering and programming that eventually helps build the quantum workforce. On the Albert side, which we have also referred to both as octant and now mostly in our exact inertial sensing platform, that's a set of technologies that has enabled users to understand at very high levels of details AMO physics, atomic physics at very low temperatures, ultra cold matter. And this is a very exotic realm of physics where a lot of people's intuitions, including my own, stop working about how is matter supposed to behave. So for instance, Bose-Einstein condensate, or BC, is perhaps the exemplar of this, where it's the fifth state of matter, and it behaves very differently than solids, liquids, gas, plasma, etc. And what we've been able to do, both through a simulator, which is open source and accessible to the broader community, I think Octopi, if people Google that, is the name of the simulator.
I'll try to put a link down below.
Cool. And then also general experiments that we've run on previous iterations of our hardware have been accessible over the cloud. Today, a lot of that has shifted into the landscape of inertial sensing as well as gravity gradiometry, which is highly related. And so I think for those who are interested in kind of the broader outreach here, stay tuned on how we work with NASA, which is another wonderful partner in terms of outreach. And we just announced, I think I mentioned this earlier, that we're putting a quantum sensor in space. A lot of the tutorials we put out, which are openly accessible in the simulators, which are accessible to, are effectively the gateways to understanding the experiments that NASA is going to be doing using quantum sensors in space. And then the last thing maybe I can add just on the quantum computing side is we have assembled a few different YouTube collections on our own channel, and those might be interesting to the group too, especially if they ever go to schools and want to show off kind of some fun animations of how quantum computing works, how atomic clocks work, et cetera. We do think that building up the workforce for the next generation is a really important part of how we collectively work to make quantum a real thing. And so always happy to support outreach efforts.
A little bit of extension on that outreach. So you directly mentioned school, like elementary school and high school. Are you guys, so there right now, the statistics I've read is that there is a lack of 7,000 quantum worker, like there's 7,000 open jobs in the quantum workforce. And it's supposed to, the quantum workforce is supposed to go up to like 100,000 or something ridiculous like that by 2030. Are you guys concerned about that? And do you have any like direct to like college or junior colleges? Because a lot of these are going to be technician jobs. Any plans for that?
Yeah, sure. So absolutely, there's a dramatic workforce shortage, and we've been working both in the Illinois ecosystem, which I'm part of, and Colorado ecosystem, and also we have an office in Madison in the U.S., as well as our international offices in the UK and Australia, on working with local universities, also local associates college program, community colleges, et cetera. In this office in Chicago here, we work a lot on software, but we've announced a significant expansion of our efforts in the state in conjunction with the IQMP Park, where we will be bringing a quantum computer to the state. And so in that spirit, we've started to think about apprenticeship type programs, starting with the universities that we're most familiar with, University of Chicago, internship programs. For the last 4 years or so, we've hosted almost every summer interns from UChicago. And I know QuantiCAD has as well, which is exciting. And so that's part of where we've started. I think in the software world, it's a little harder to do kind of some of the apprenticeship type programs, but on the more hardware side, technician type training programs are definitely of interest to us. And the exemplar I've give is, in the past, we've had an employee who came from the cake baking and cake decorating world who turned out to be one of our best solderers. And so that's just one of the examples of success stories of how skills can be very transferable to the quantum world. One doesn't necessarily have to understand a thing about Schrodinger's wave equation to be able to contribute in very significant ways to the quantum industry.
Yeah, I completely agree. Okay, so last question. It's a little random. I've read that you're a bit of a pizza aficionado. I'm also into home pizza. I've got like one of the small ovens out. I don't remember. It was like one of the cheap Amazon ones, but it's propane powered, and then like it's outside and heats it up. And I was wondering, like, what's your pizza philosophy? Like Neapolitan, New York, Detroit, and like what do you think is the most important thing when making pizza?
Ooh, wow, what a good question. So I love pizza, and glad you do too. And in the past, I've been a total Neapolitan pizza purist. There's no other pizza I recognize kind of thing. I've grown up and changed my tune on that. When I was in that realm, it was really only Neapolitan, only margherita pizza or bust, the double zero flour, the mozzarella bufala, etc., San Marzano tomatoes, just the premium ingredients. Honestly, since then, one thing that changed was moving to Chicago, where I initially in my first few weeks was like, oh, I can't have that terrible casserole thing they call pizza. But after being a grad student who attended our Friday happy hours, and it's a nice place to get $1 gigantic slices of deep dish pizza at Chicago, that was the moment of maybe, honestly, maybe the price did it for me of getting an entire like gigantic meal for $2. I really developed a love for deep dish as well. I'm a Lou Malnati's fan. And do you have a deep dish favorite?
My favorite's Giordano's.
Giordano's, yeah.
Illuminati's and like Rosati's. And,
yeah, we can still talk. We can still, as viewers may know, there's a lot of bitter hatred in the Chicago over like preferences on deep dish. But I think that helped me grow up in terms of being accepting to other worlds of pizza.
Yeah.
So these days I'm not too much of a purist in terms I do love my Neapolitan. In Chicago, my favorite restaurant is Nella in Hyde Park, and that's a Neapolitan place. The owner, Nella, Chef Nella, is from Naples, so she's very legitimate. But I do like deep dish from Lou Malnati's. Detroit style was newer to me, but in fact, I met my wife at a Detroit style pizza place in Chicago, so that has maybe some sentimental value to me too. And then New York style, I love too. I think that probably is honestly, growing up in Maryland on the East Coast, going to Sparrow's, the mall, is probably what kickstarted my interest in pizza. So that has a special place in my heart too. I have never had somehow New Haven style pizza yet, so that's kind of next on my list of desired pizzas.
Yeah, I like Detroit because it's so easy. It's the one where you don't have to think about it at all. You're just like dough, cheese, sauce in the oven. And honestly, like it's one of my controversial opinions. Most controversial opinions is that I think the optimal pizza is dough, cheese, and then the sauce, because that way like the dough cooks perfectly rather than like taking a chance. And maybe it's me like being lazy about pizzas, because like if you do it the other way, then you have to worry about like the center cooking all the way, while like the outside, the cheese not burning, and like having that race going on, the whole that three-dimensional differential equation trying to like solve.
Interesting. I will have to try that sometime. That does sound like a pretty controversial opinion, but I see your reasoning and the merit to it.
Yeah. Okay, well, this has been Pranav Gokhale. Thank you so much for taking the time to talk to us. Yeah, we'll see you then.
Thanks so much. I really appreciate it.